Well, good evening, ladies and gentlemen, and welcome to tonight's program. Tonight, we're going to consider a difficult subject. I don't think you're surprised at that. We're going to consider the limits of human understanding, with a particular focus on mathematics. Now, this is a science festival, and science is the most reliable way of gaining knowledge and understanding of the world. In the last 4 centuries, we've seen great advances in our understanding of both the physical and the biological worlds. But what are the limits of this understanding? This is a question philosophers have pondered over the centuries, traditionally worrying about areas such as the validity of induction, that is, inferring generalizations and general laws, or the reliability or even the validity of our senses in generating information about the world. Now, tonight we are likely to touch on such philosophical issues, but our main focus will be on mathematics and on mathematical logic, because mathematics and mathematical thinking underpins much that is important in science. It's been the cornerstone of physics since the 17th century, particularly since Isaac Newton. Indeed, some aspects of physics, particularly 20th century physics like quantum mechanics and theories of the ultimate structure of matter, only make sense in terms of mathematics. They are not part of our common sense world. Turning even to biology, in the last 50 years, it's gradually being realized that DNA is essentially a digital information storage device, and it's become clear that the way information is managed in living systems will be key to biological understanding. It's my own view that given the complexity of biological information and its management, I wonder if we may not end up in strange places analogous to quantum mechanics in physics. But as well as underpinning science, mathematics and logic appears to be the most secure sphere of human understanding. It's based on a firm structure of axioms and of proofs. It seems to be a most reliable and self-contained part of human knowledge. But tonight, we shall see that this is not quite as straightforward as it seems. Godel, in the first half of the last century, showed that mathematics was not always provably consistent. In fact, some mathematical facts can never be proven to be true or to be false. They are mathematical paradoxes, analogous to literary paradoxes. Maybe, therefore, the relationship between truth and mathematics is more tenuous than we thought. This, ladies and gentlemen, is our territory tonight. So let's begin with a video about Godel.
In 1920, amidst the wreckage of war-torn Europe, David Hilbert, the most influential mathematician of his time, issued a call to scholars everywhere to prove the consistency of mathematics.
The country is in ruins in a lot of ways, and so part of what they're seeking is emancipation from that. And they're seeking a vehicle to the future, where science and math was going to be the promise of a golden era. A lot of the mathematicians at the time really believed that they would be able to prove what Hilbert asked of them, which is that mathematics and arithmetic was going to be provably consistent. And so it was really quite a blow when a young and soft-spoken, gentlemanly student from the university comes and declares that actually it's not true.
It was a 24-year-old doctoral student named Kurt Gödel who exposed the limitation of mathematics. His ideas would shake the very foundations of mathematics and philosophy.
The culmination of Gödel's ideas are called the incompleteness theorems. There are mathematical facts that we can never prove are true or false. There is no such thing as a mathematical theory of everything. and they are one of the most significant results ever to be proven in mathematics. Godel wasn't completely well. He was a severe hypochondriac, bordering on paranoid schizophrenia. He had bouts in mental institutions. Numbers, mathematics, he believed was real. He wasn't so sure about the truth of his senses and perception of reality.
By 1939, with Europe descending into a Second World War, Gödel fled Vienna for Princeton. He was invited to become a permanent member of the Institute for Advanced Study.
Godel in some ways was very charming and very gentlemanly, but he was also extremely reticent and very withdrawn at times. He had this deep devotion to truth, and he was his own thinker in that sense. Nothing would sway him. And one of his very few friends was Einstein. Einstein, while being a very different person, also had a similar incredible independence of mind. There must have been a way in which they respected each other on those grounds, where they could see in each other, that complete independence of mind.
Though no one understood the nature of their friendship or the depth of their conversation, toward the end of his life, Einstein felt that his own work no longer meant much. He came to the Institute merely to have the privilege of walking home with Gödel. In the end, paranoia and an obsessive fear of being poisoned led Godel to starve himself. He died in a Princeton hospital weighing just 65 pounds at the age of 72.
I think in his fear and anxiety about his physical life, the physical pain he felt, the paranoia about his health, his dream was that it was a reward to, in the next life, be presented with a pure, more platonic reality. He was a very tragic figure.
Good. So, could I ask the panelists to come out on stage, please? So I'm just going to say a few words about each of them, starting with the gentleman immediately to my left, Gregory Chaitin. He is a mathematician and computer scientist, chief architect of algorithmic information theory, which relates to the computing of complexity. He's also the discoverer of the omega number, and we may hear more about that later. He's at the forefront of the emerging metabiology field, which regards life as a sort of biochemical software. He's the author of a dozen books about mathematics and philosophy, including Thinking About Godel and Turing. He worked for many years at the IBM Watson Research Center in New York, where he is currently emeritus. Just to his left, Rebecca Goldstein, a philosopher and author. As a philosopher, her areas of speciality are philosophy of science, mathematical logic, and 17th century rationalism. Her first novel, The Mind-Body Problem, more novels followed, but among her works of non-fiction is the biography of incompleteness, The Proof and Paradox of Kurt Gödel, chosen by Discover magazine as one of the 10 best science books of 2006. Her latest novel, and I've read this one, is 36 Arguments for the Existence of God, a work of fiction. She has been a professor of both philosophy and of writing, and is currently in the Department of Psychology at Harvard. To her left, Mario Livio, senior astrophysicist, head of the Office of Public Outreach at the Space Telescope Science Institute, responsible for the Hubble Space Telescope. An author of award-winning books, including The Golden Ratio, The Story of Pi, The World's Most Astonishing Number, and Is God a Mathematician?, selected by the Washington Post as one of the best books for 2009. His research focuses on supernova explosions and the nature of dark energy. And finally, on his left, Marvin Minsky, one of the pioneers of artificial intelligence. who's made numerous contributions to the fields of AI, cognitive psychology, mathematics, linguistics, robotics, and optics. He has talked about the human intellectual structure and function in his books, The Emotion Machine and the Society of Mind, and also built the SNARK, the first neural network simulator. His other inventions include robotic devices, and he is the recipient of numerous prizes and awards for his work. Dr. Minsky is a professor at MIT, where he co-founded the Artificial Intelligence Lab. A great lineup, and welcome to all four of you. I want to start with Rebecca, if I could. I wonder if you could tell us a little bit about Godel and also the environment in which he was living, the intellectual environment in Europe following the First World War.
Well, he was born in Brunn, a Czech town. His family spoke German, and he came to Vienna in the 20s. And Vienna, at that time, was a city of extraordinary intellectual and artistic fervent. Tremendous amount of rethinking from the foundations up. Things had not worked out so very well, World War I, and there was just a sense of having to begin anew. And one of the centers of this thinking was a place that we know. I actually kind of think of Vienna as sort of the New York of its day. You know, it was kind of, everything was happening there and very much not in sync with the rest of the country. Well, you were Viennese, and like you're a New Yorker. And it was something that we now call the Vienna Circle. And it was a group we now associate with a movement in philosophy and in science called logical positivism. And this was a movement that was trying to, again, think things through from the bottom up, make things very, very clear. So they had a criterion for meaningfulness, that the meaning of a proposition is given by the conditions that would verify it. And if there are propositions that no experience would count for or against, it was a meaningless proposition. So meaninglessness was a term of damnation that they used very, very often. And this was a center, this circle of, there were scientists, there were philosophers, there were mathematicians, and there were two young graduate students. They had been invited by a mathematician who was a leader of the Vienna Circle, Hans Hahn, and he had two graduate students, one of whom was named Kurt Gödel, and who was a very, very quiet man and didn't say very much. This group was also reverentially in awe of Ludwig Wittgenstein. Wittgenstein was their hero. He was their god. And they had a certain view about the foundations of mathematics, what made mathematics true. They hated mystery, and mathematics presents a certain degree of mystery. How do we know it's true? How do we, it's a kind of certainty and incorrigibility and infallibility. How does it come to the likes of us? Is it descriptive? Are we just making it up? They had a certain view of mathematics given by David Hilbert, formalism, and that's why they attached the word logical to their positivism, and they were embracing Hilbert's view. And this was the environment in which this young Gödel sat there, keeping his counsel, not really speaking. He disagreed with them entirely, but he didn't say it until he had a proof. Incompleteness.
And what was that proof?
Well, so the big mystery, of course, in mathematics is what's it all about? There's a certain degree of mystery here because it's not empirical. It's not going to be revised in the face of anything further that we're going to learn about the world. That's why mathematicians are cheap to hire. They don't require observatories. They don't require laboratories. It's all in the cranium. And it's done a priori, a proof from principles, from first principles. And so the question is, and the way I often think of it is, that old the other Marx, Groucho Marx, joke that I wouldn't have any club that would have me, I wouldn't want to belong to any club that would have me as a member. I mean, in mathematics is, how did we get invited to join this exclusive cognitive club? How do the likes of us have this kind of certainty? Are we just making it up? Are these just stipulated rules? Is it just a higher form of chess? That was the formalist school. Or is it descriptive of something? Gödel tried to put forth a theorem, a mathematically proved theorem, rigorously proved, that would address this meta-mathematical question. So that's the interest of this thing. That's why it seems to be mathematics that spills out beyond mathematics, that tells us something perhaps about the nature of mathematical truth, the nature of knowledge, the nature of us as knowers, perhaps, right? Here's what it actually says. I mean, there are two of them, and the second one follows as a corollary from the first. So here's the first. In any formal system, you might want me to go on and define what a formal system is.
Tell us what a formal system is.
Formal system is something that is stipulated by rules. You stipulate the axioms, you stipulate the alphabet. Here's the alphabet of this thing. You stipulate how you can combine the alphabet into meaningful things.
Baseball is a formal system.
Yeah, and you don't worry about what it all means. It's something that's purely computational. A formal system is something that's mechanical. It's rules. It could be programmed into a computer, perhaps. It's a purely computational, mechanical way. You don't have to worry about what it all means. That's a very vague, informal description of what a formal system is. In any formal system, and what formalism wanted to do was to reduce all of mathematics to formal systems, to just show it's just a purely mechanical thing following from stipulated rules. In that way, dispel the mystery. Okay, Gödel's first incompleteness theorem. In any formal system that is rich enough to express arithmetic, there will exist a proposition which is you can express, which is undecidable, meaning neither it nor its negation can be proved in that system. Another way of saying this, a little more controversial, is that in any formal system rich enough to express arithmetic, there are true propositions that can't be proved. And the second incompleteness theorem, which which everybody saw the relevance of immediately because of what Hilbert had said needed to be done, proving the consistency of arithmetic. The second incompleteness theorem, which is a corollary of the first, says one of the things that you can't prove in a formal system is the consistency of that system. And consistency, again, informally, what this means, a system is inconsistent if you can prove for some proposition P, both P and not P. That is an inconsistent system. Inconsistent systems are useless because anything at all follows from a contradiction. So if you've got a system that can prove a contradiction, you can prove absolutely anything, the existence of God. I mean, anything. You can just prove anything from an inconsistent system. So Gödel's second incompleteness theorem, saying that within a system you can never prove the consistency of that system, really was a blow to formalism.
It really sounds rather shocking, to me. How did the Viennese, or for that matter the rest of the world, take to this?
Well, the very interesting thing is that when Godel, so he had formed these he had these huge beliefs, Platonism. He believed that mathematics was descriptive of a trans-empirical realm. He wanted a mathematical proof that he felt was going to prove something mathematically, an audacious ambition that he may or may not have carried through on, but he certainly did something big. And he announced it at a conference in Königsberg, very softly mumbled it on the last day. He said, it might indeed be possible that there are true propositions of the order of Goldbach's conjecture and Fermat's last theorem to very important unsolved problems. And in that day, Fermat's last theorem has now been proved by Peter Wiles. But that there might very well be that for every formal system, there are true propositions of that order that can't be proved. He kind of mumbled it. That was the announcement of this incredible discovery, and nobody paid him any mind at all. And in fact, when the proceedings of that conference was written up in Erkenntnis, an organ of logical positivism published in Berlin, it wasn't even mentioned. Nobody even mentioned this. But there was a great mathematician, John von Neumann, who was there at that conference. He was standing in for David Hilbert. He was presenting Hilbert's formalism. And he came over to this young, shy mathematician afterwards, and he said, wait a minute, did you just say what I thought you said? And he spoke to Gödel enough so that he thought there's really something here. He went back to Princeton. He was at the Institute for Advanced Study, started to think some more, wrote to Godel and said, it seems to be that if a consequence of your first theorem is that you can't prove the consistency of arithmetic. And Gödel wrote back and said, oh yes, you've got it right. I have the very formal proof here, a very rigorous proof here. And it was von Neumann who spoke up incompleteness theorem to everybody. And he was the one who disseminated it.
Gregory, you also have an incompleteness theorem. Can you tell us right, from the horse's mouth what it's all about?
Yeah, sure, Paul. 80 years later, we still don't know what the hell Gödel proved. The problem, you see, the normal idea is mathematics gives absolute certainty. It's pure thought. If there's any place that there's certainty, it's in the world of pure thought. And in 1931, Gödel pulls the rug out from under that. So what the hell is mathematics? And it's 80 years, and we're still arguing. So the fallout has not stopped. The earthquake is still, there are still tremors. Now, my own effort to understand what's going on, I've been using ideas that you refer to in your introduction of complexity, ideas that come from biology in a way, inspired by biology, but I've been using them in mathematical logic. And so with a notion of complexity or information content, I can show that the world of pure mathematics has infinite complexity or contains an infinite amount of information. But any mathematical theory only has a finite amount of complexity. So that makes incompleteness seem natural. Another way to look at it is I have a number called omega, which comes from Turing's halting problem. But it's sort of like the DNA for pure mathematics. And this number is a concrete example showing a place in pure mathematics where there's infinite irreducible complexity. The omega number, if you write it in binary, each bit is a complete surprise. It looks completely accidental. And this is a very concrete example showing that pure mathematics contains infinite irreducible complexity. So these are mathematical facts that seem to happen for no reason, and it's an infinite number of them. So what I'm starting to think now is that...
Do you mean by that you can't predict? I mean, you can't predict what's coming next if you...
You can't predict what's coming next. You can't prove what's coming next. It looks like God is tossing a coin in mathematical truth. Now, as a Platonist, I think each bit is determined. Nobody is playing dice with mathematical truth. But to us, it looks that way with any of the mathematical tools that we will ever have. So this is a place in pure mathematics where things look accidental, where they really escape are beyond our powers. Now, what I'm beginning to think is that this is opening a door to biology. I'm beginning to think that what Gödel and Turing in 1936 came up with was the first step in the direction.
This is Alan Turing.
Alan Turing,
Yeah.
1936, right. But what the door was opening, taking pure mathematics in a new direction, which I feel is the direction of biology, actually. I think history may say this in 50 or 100 years. Because, you see, if you look at the omega number, what it shows is that pure mathematics contains infinite irreducible complexity. Now, normally people think that the field of science where there's complexity is biology. Biology is the domain of the complex. There are no simple laws, right? But mathematics and physics are supposed to be simple, governed by beautiful, simple equations. So what Gödel and Turing opened the door to is the fact that, in fact, pure mathematics has infinite complexity, and in a way is even worse than biology, because biology has very large complexity, but it's only finite. So pure math is even worse. And based on this hint, I've been trying to study the fundamental ideas of biology in an effort to come up with a theoretical biology, which is very hard, in fact impossible. So I'm trying to do a theoretical metabiology, which is, instead of trying to have a theoretical mathematics for real biology, which is just too messy and complicated, it's hopeless, I'm trying to see if you can come up with a mathematical toy model that captures some of the essential ideas of biology. And it's a software model, and the basic idea is very simple. I'll summarize it in two phrases. Well, you said it. DNA is digital software. That's the basic idea. So I'm running with that idea as a mathematician. And the two phrases that define this metabiological effort that I think is promising but is just beginning is to look at biology with, through the evolution of mutating software is one of the key phrases in metabiology. And the other key phrase is random walks in software space. So I'm going to just wave these mysterious words in front of you and say, come back in 50 years and maybe there'll be a field of mathematics there.
Well, I might come back in 15 minutes to that, actually, but we'll see how much progress we've made in that time. But both of you mentioned the Platonists, and I think it might be interesting to get a sense of realism and non-realism in mathematics. Would somebody like to pick up on that? Explain what it is?
Well, I'm happy to talk about Platonism versus formalism that she mentioned and so on, and what are these things. So Plato is, Alfred North Whitehead once wrote that all of Western philosophy is a series of footnotes to Plato. So he was a very smart person.
Yeah.
But maybe it's best, what he thought is maybe best explained by his allegory of the cave. He said that we humans, are like prisoners in a cave. Somebody is throwing shadows on the wall of the cave. The prisoners are forced to see the shadows, and that's what they think reality is about. So Plato basically said mathematics exists in some world out there. This is a Platonic world of mathematical forms. So when I draw a circle on a piece of paper, that's not the real circle. The real circle is in that world of mathematics. This is just a crude approximation for that circle. Most working mathematicians are Platonists in their hearts. Namely, they think that mathematics has this existence out there, and we're merely discovering the truths of mathematics. The school that Rebecca described before of the formalists, she actually used this analogy of chess. Basically says, no, it's all just, I write down some rules or some set of axioms, and I can derive all of mathematics from that. It's like, I give you the rules of chess, we play chess. I change the rules, we play a different game. Basically, the idea is I write down one set of axioms, I get some form of mathematics. I change the axioms, I get another mathematics. And the best example of this was the Euclidean geometry that we all learn in school. It was based on a set of 10 axioms, one of which said that if you have a line and a point outside the line, you can pass a single parallel line to that line. That was thought to be truth from God until the beginning of the 19th century, when 3 mathematicians independently showed that actually you can dispose of that axiom altogether, and you can develop new mathematics, one that can be described on a surface curved like a saddle, one on a surface like a sphere, and so on, in which this axiom doesn't hold true at all. And those are equally good descriptions of space, you know, and everything. So basically, formalists say, write down the axioms, give me what there is. What Gödel did was that he pulled the rug underneath this entire premise. Because basically, you know, to summarize in one sentence what Rebecca said, he basically showed that no formal system, no system of axioms you're going to write are going to ever capture all the truths of mathematics. This is a simple way of saying this. You know, in physics, I'm a physicist, people here may have heard the term theory of everything. We strive to get this theory of everything in physics. What Gödel's theorem shows that there is no theorem of everything in mathematics. Namely, you cannot, you know, write down some set of axioms and from that derive all of mathematics. So these were the tensions between these particular groups. On top of that, there was this third group, which is that of the logicists, which is people like Bertrand Russell, Gottlob Frege, and others said, no. It all actually comes out of logic. I can write down some axioms of logic. For example, I tell you, either the butler killed the millionaire or his daughter killed him. And then I tell you, the daughter didn't kill him. Then you have to conclude that the butler did it. And this conclusion is not dependent on how old is the butler, what's the length of the nose of the daughter, or any such thing. So there are some axioms of logic, and Gottlob Frege said that he could prove all of arithmetic, and by that I mean even 1 + 1 = 2, from some axioms of logic. And that looked extremely good. I mean, you know, this was, almost everybody was happy. Because, you know, the formalists said, okay, it's all a game, but maybe there is a mother of all games. The Platonists said, oh, if it all comes from some axioms of logic, surely those are somewhere there in that world of mathematics, you know, and so on. So all of this looked very good, except that when Frege was ready to send his fat book to the print, Bertrand Russell sent him a paradox, which is a little bit like what is sometimes called the barber's paradox. You know, there's this barber who has this sign, I shave all and only the men of the village who don't shave themselves. And this all sounds perfectly logical because the men who shave themselves don't need the services of the barber, and the barber shaves everybody else. Until you stop and ask, okay, but who shaves the barber? And if the barber shaves himself, he's one of those men that shave themselves, and therefore he doesn't shave himself. If the barber doesn't shave himself, then he's one of those that don't shave themselves, and then he has to shave himself. So the paradox that Russell sent to Frege was not quite this paradox, but it had a similar flavor to it. And so it basically showed that our logical system can be fallible. So there was this crisis. You mentioned shock, you know, in Gödel's theorem and so on. There was a sense that the whole foundations of mathematics became rather shaky. And this is what for me as a physicist makes the puzzle even bigger, in the sense that still, while these foundations were shaking of mathematics, mathematics became this extraordinarily powerful tool in explaining the universe around us. So how can you explain the whole universe with something that has such shaky tools? I spoke a little bit long, but I hope this...
Well, I'm going to pick you up on that in a moment, that very point. But does anybody else want to comment more on this realism, non-realism, Platonism business?
I have a whole bunch of remarks about, but they're a little tangential because I'm going to talk a little bit about the limit of public understanding. Because all sorts of remarkable things are happening in science. And there are a few directions in which the public has been misinformed in a strange way. And the result has been some strange beliefs. So let me mention one. This is a little different, but you've all heard of the uncertainty principle and the mysteries of quantum mechanics, and many philosophers who know a little physics have explained to the public that the world of Newton, in which things were determined and mechanical and predictable, was really a nice beginning in physics, but the real physics is very different and things are uncertain, and there's a famous Heisenberg principle that you can't know the position and velocity of a particle both at the same time, but only the more certain you are of one, then the less certain you are of the others. And that's perfectly true, but the numbers are very strange because these quantum effects in most cases are very small. So here's the joke. Suppose we take the world of Newton and talk about the kinds of things that Dr. Chaitin is interested in, evolution and genetics and so forth, and think of a little molecule of DNA. And as everybody knows, that's the code which determines a lot about how biology works. Well, if you take the world of Newton and look at the solar system, that's sort of like an atom. There's a big star and little planets going around it. And then we know from about 1900 that atoms are the same sort of thing. There's a nucleus and little electrons going around it. But the joke is that things like solar systems aren't stable. So in the world of Newton, for example, some of, I think Sussman and Jack Wisdom at MIT some years ago showed that probably in the solar system that we live in, Jupiter is so large and has such a big gravitational field, and Pluto is so far away from other things that in a few billion years, probably Jupiter will throw Pluto out. So it's not clear how long the solar system lasts.
It won't be such a big disaster. It's not a planet anymore.
That's right. But on the other hand, if you think of a molecule of DNA at room temperature, that's stable for 1 billion years. And so this is why evolution is possible, because of quantum mechanics, not in spite of it. So that's just one. In other words, the public has been told that in modern physics things are much vaguer and uncertain, and it's exactly wrong. In the Newtonian world, you couldn't have the kinds of stable structures. Well, there are about 5 more, but here's another one. We all learn about evolution, and there are some people who say, well, how could random changes and the kinds of variations that Chaitin's talking about lead to anything so magnificent as people with all their intelligence and mathematics and philosophy? How could that have happened when we're just making random changes and selecting them? Well, have you ever thought about it? There's a problem with evolution, as it's explained, with Darwinian evolution. I'm not saying it isn't true. It's absolutely true. But there is a little trouble with it. Namely, the way evolution works is you make little changes in organism, generally random, although not always, and then some of them live and some of them die because the ones with the wrong kind of toes fall out of the trees and get it, all sorts of bad things happen. What does evolution remember? It remembers the things that worked, but it forgets what killed all the others. There's no record of that. And so when it comes to intelligence, it may be that you couldn't evolve a brain with Darwinian evolution alone. But I'm not being Mysterian here. I'm just saying the answer is language, culture, society. Maybe some chimpanzee-like creature gets a few words or a few symbols. And what do we tell our children? Well, if you look at the fairy tales, I think the first great psychologist really was Sigmund Freud, who had this idea that the mind is many parts and very complicated. And one of the things Freud talked about is early experiences having big effects. Well, look at the legends that populate all cultures. Almost all the legends like the Three Little Pigs and so forth, are about mistakes you can make, and they're usually fatal. And the answer is a human child would never survive without a culture because it wouldn't live long enough to learn all the fatal mistakes that are common. So I could go on, but what I'm saying is that when we talk about the limits of understanding, I think we need to know much more about how human understanding itself evolved and develops. And my feeling is that we're just at, one is always making fun of ancient people and their foolish legends. And I think we're just coming out of one of maybe 20 different levels of ignorance going into the next one. And we're learning more and more every year.
Well, one thing I always feel ignorant about, I must say, or find difficult, is what's called the unreasonable effectiveness of mathematics in explaining the world. I never quite know why that should be the case. Can somebody help me?
Sure, yeah. So the phrase, by the way, was coined by Nobel laureate Eugene Wigner, the unreasonable effectiveness of mathematics in the physical sciences. There is, by the way, a paper entitled The Unreasonable Ineffectiveness of Mathematics in Biology. But in the physical world. So what is meant by this unreasonable effectiveness? So let me give you just a couple of very quick examples. So there was this astronomer, Johannes Kepler, and he made observations 400 years ago, and they were not very accurate. They were accurate for his time, but not very accurate. They were accurate to within about 4%. Yet from those relatively scanty observations, Sir Isaac Newton managed to write a mathematical law of gravity that already by the 1950s was shown to be accurate to better than 1 part in a million. In fact, in an experiment done in 2008, they showed that the law, inverse square law of Newton, holds down to a distance of 56 microns. 1 micron is 1/1,000,000th of a meter. These are distances that Newton could have had no idea his mathematical law should hold true. What is it that gives mathematics such powers? We have a theory of everything that's electric and magnetic. It's called quantum electrodynamics. In this theory, it's a very highly mathematical theory. You know, electrons that move in atoms, they are like little magnets. You can use this theory to calculate the strength of this magnet. We can calculate the strength to parts per trillion. Everyone now knows what a trillion is. It's the size of our annual deficit. You calculate this magnet to parts per trillion. In 2006, this magnetic strength of the electron was measured to parts per trillion. And the two results agree to within 8 parts per trillion.
But Mario, why are you surprised? The world is built out of mathematics. God is a mathematician. So this is the most natural thing.
I wrote a book with this title, but with a question mark at the end.
Because you're a physicist and I'm a mathematician.
So the question is indeed, how come mathematics is as powerful as it is? In particular, there is this thing which I sometimes call the passive effectiveness, which is mathematicians sit down, you know, people like Marvin, like Gregory here, they sit down and they develop branches of mathematics sometimes with absolutely no application whatsoever in mind. In fact, they are proud that there are no applications. And yet, sometimes decades, sometimes centuries later, those very precise branches of mathematics are found to be exactly what is needed to theory. You know, this was the case with Einstein's general relativity. This was the case with group theory, you know, and so on. So these things exactly provide this. How come? Why is mathematics as powerful as that?
Mario, then Marvin. Or you can do Marvin. Do you mind being interrupted?
No, absolutely
Marvin.
not.
Well, I think I have one funny answer to that, which is that let's think what would happen if it weren't, if the world didn't obey simple principles. And the answer is, do you think the world exists? People argue. A lot of religions are based on the idea that, well, here's the world, somebody must have made it. Of course, then you have to ask the question not just how does the world work, but How did the creator work? But the real problem is that the word existence doesn't make any sense. It's all right to say this table exists because that means this table is in the universe. It doesn't make any sense to say the universe exists. So my argument is, one, this is just a possible universe. And now let's consider all the possible universes. And suppose you had a universe in which energy weren't conserved. Then all of a sudden things would blow up. And DNA wouldn't last 1 billion years at room temperature. And so if you take all of the things that physicists say, look at this amazing mathematical thing, it's accurate to 1 part in 10 to the 16th, then you say, well, what would happen if it weren't? And if you look carefully, you'd see that, well, then everything would explode or everything would disappear. And in fact, the current theory is that once in a while, some little thing, in fact, does explode, and that's a big bang, and another possible universe.
This is multiverses, is this?
So,
multiverse?
So in other words, maybe you don't have to answer this question because the answer is obvious. In worlds where there are no laws, there is no DNA and no philosophers to discuss it.
So let me just say a few things about
I only read half your book, and
but you read the right half. You read the right half. So let me just say a few words about this. So because I wrote about the multiverse and things like this. So let me just say a few things. So Marvin is absolutely right in the following statement that he makes. He talks about a world in which there are no laws of physics, or the laws of physics are very, very different from what we know them, and so on. It is certainly the case that if there were no laws of physics, we might not have existed here. And furthermore, we wouldn't be talking about describing those laws of physics by mathematics. I mean, the fact that our universe is symmetric in the sense that, for example, an atom here behaves the same as an atom 12 billion light years from here, this is what allows us to try to explain anything. Otherwise, we wouldn't be here. Now, that, however, still does not answer the question, why is our mathematics so adequate for describing the laws that exist? And how come that mathematics that are built with absolutely no application in mind turn out to be very descriptive of physical phenomena? But the answer there is actually, it's complicated, but it is not that difficult to understand. It's a combination of many things.
Mario, the world has to be built out of something. Why not out of mathematics? That's the most beautiful thing we have. What do you have against my reason for all of this? The world is built out of pure mathematics. It's the most beautiful, the most fundamental thing that exists. It has the most beautiful structure. Obviously, God, or the great computer programmer who made this simulation we're in, would use that beautiful stuff. Right? What else would you make the world out of? Marshmallows?
So here's another possible explanation, and that is that our science, starting in the 17th century, what physics did was to isolate structure, and how do we describe structure in the language of mathematics. And so our laws that we've been able to formulate so far have all been structural, therefore mathematical, but are not getting at everything, so that there are certain problems. For example, my favorite being the hard problem of consciousness, right? That we have not yet been able to tackle. It's not just that we can't tackle it. You might be disagreeing with me here, but we don't know how to tackle it because we're using this kind of our notion that we've gotten from physics of what a law is, which is an isolating structure that we can express mathematically, but isn't it's an incompleteness. It's another incompleteness theorem. It's not exhausting the stuff of matter. And so that would be another explanation for why we see laws of physics are always mathematical. Those are the only ones we can get at. We have the tools to get at that.
I'm giving up chairing. I'm just
let,
going to
let me try to weave together some of what the three of them say. So Rebecca now touched something that is really very important, which is one of the things is that these are the things that we have at our disposal, and Gregory touched about that too. So we try to use them the best we can, and not only that, we try to actually tailor the mathematics we use a little bit to the problem at hand. For example, if I were to put pebbles into this bottle, and I would put 3 pebbles, then 4 pebbles, then I would be using arithmetic to describe what happens, right? 3 plus 4 equals 7. If, on the other hand, I pour water into this bottle, I pour 3 times water, then 4 times water, I wouldn't describe arithmetic to it. I wouldn't say there is 7 water in this bottle, right? So we tailor the mathematics that we use a little bit to the type of physics we want to solve. Then we touched upon this thing that not everything can be described by mathematics, and Marvin here described
Why
the
not?
fact. Well, I'll tell you why. Let me tell you why.
You know, Gödel would not like the way you gentlemen are arguing. As Rebecca points out in her beautiful book, Gödel is a man from the Middle Ages, and he was against empirical science. He said pure mathematics is the only field which conserves medieval theology, essentially, which conserves idealism and Platonism, and he didn't believe in empirical science. All truths should be a priori truth, necessary truth, right?
Well, I think
right? So you gentlemen have a very, how do you say, an attitude which is quite common now, an empirical attitude. The word God can't be mentioned, mathematical beauty can't be mentioned. But Gödel belongs to the Middle Ages, you know, and he would be very uncomfortable. So I'm trying to
let me say something.
Tell you what Gödel might have responded
but
to all of this.
Let me take the example that Marvin used. Yeah, but you know, Godel lived a few tens of years ago. We have advanced since then. I'm talking about something that we know how to write equations for, okay? I want to describe what every atom in the atmosphere is going to do. So it sounds simple, right? I know the equations. If I just have a big enough computer, I'll be able to calculate that. Guess what? Not true. And you know why? Because you will need as an input to that computer to put the position and the speed of each atom when you start the calculation. Now, quantum mechanics tells us that I cannot tell precisely the position and the speed of a single atom, let alone of all the atoms in the atmosphere. Yet the system is chaotic, which means it is infinitely sensitive to initial conditions. You change the position of one atom by a little bit, and the final answer is completely different. So there are problems where quantum mechanics and chaotic systems tell us that we will never be able to calculate. But we are able to try to address fundamental problems in physics, and there I agree with Gregory completely. Mathematics is our most beautiful tool to do this. That's what I do for a living. I use mathematics to try to explain the universe.
Well, I would like to go back to this consciousness, because I think that's a very strange situation, because the word consciousness, it's an old word, and I think it's a social word. If you look in my book, I have something like 26 different meanings for the same word. And the reason consciousness is considered a mystery is because the philosophers who talk about it don't recognize that they're using it as a trash basket for 26, or I forget the number actually, of different problems about psychology that they don't understand. If you look in early Freud, he's saying that consciousness is the collection of activities that result when there are conflicts between basic instincts and higher level constraints, between what the individual wants and what a culture wants. And Freud's model is very complicated. It doesn't just have a conscious. He does use the word, and he has a pre-conscious, and he has sensors and facilitators that act at the gates. But the mystery of consciousness that it's very popular nowadays. People like Stephen Harnett and other philosophers make a big fuss about it. But as far as I can see, they never look at that word and see that this is just all the mysteries, that all the things about higher level thinking that they don't understand. Giving a single word to it, of course, makes it seem like a big question, a very hard question. But if you break it into 26 easy questions, which in chapter 4 of the emotion machine, then you've got a lot of things to work on, and there's no general mystery at all, as far as I can see.
Well, here's how philosophers often describe it. For example, Tom Nagel in What Is It Like to Be a Bat? For something to be conscious means that there is something that it's like for that thing to be that thing.
What do you mean,
facts
something?
of the matter. There are facts of the matter. So right now,
Is there a something it's like, or is there a lot of complicated
stuff? A lot of
stuff?
something. So for right now, for example, I'm conscious. I'm not sure about anybody else, but I am. And you could describe me. And as a novelist, of course, I do this all the time. I describe what is it like for that character to be in the world. What is the world like for that character? What does it feel like? So there are sensations, there are memories, there are emotions, there are moods.
So there are 36 things. What's the problem?
So the thing is that could you, in getting a description of that person, and purely another way of putting all of these facts, they're facts about one's subjectivity.
Your brain has 20,000 genes. Do you want it to be 10 words or 50?
But
That's
here's
silly.
the question. The question is,
what's a description?
The description of a purely physical description, as we have it now, right, a purely objective description, would you be able to get out of that the description of all that it's like to be that person at that moment, or even any of them?
Sure.
Any of them.
If it has 30,000 equations, why not? It's just
From
hard.
the equation, you could get out that right now,
What's the right now have to do with it?
Well, because consciousness is something that takes place in the right now.
It's not something. It's a word.
It's an experience. It is.
It's
the
everything
facts of what it is like to
You're
be
using
a living person.
There's no
All right,
it.
how do I put this? How do I put it without?
Yes, settle this.
Marvin, with all due respect, you can't solve a problem by declaring that it's meaningless. I know this is a popular tactic.
I said it's 20. I said it's 26 problems.
No, it didn't say it's meaningless. What Marvin is saying is that when you say consciousness, you don't mean a single thing.
Of course
There are lots of problems involved in what one tries to bury under the concept of consciousness. And if you actually try to address, please correct me if I'm paraphrasing you not in the right way, if you actually try to address individual problems which you will phrase correctly and pose correctly, you may or may not be able to find physical solutions to each one of those problems.
Yeah, let me give one example. If I might be wrong about this, but I was reading Galileo once a long time ago, and he had an expression.
It was written a long time.
Yeah, he had an expression, vis viva, or the life of motion, or whatever it means. And here's the story. He's talking about this thing, and it's 100 years before Newton, and he's got momentum, which is mv, and energy, which is mv squared, and he's using the same word. That's all I'm saying. The reason people are puzzled about consciousness is it's the difference between Galileo and Newton, and they should be using 26 words, but they stick to it and they say what's it like? There's no it. There's 26 things.
There are probably more than 26 would be my guess. There are a trillion neurons, right?
You know what we're talking about here. I mean, the fact that we're describing this in purely objective terms, in purely physical terms, a material system. And I'm not a dualist. I think that in fact we are our brains, and that our Our consciousness is a function of our brains, right?
You're using it all the time. I don't use the word.
Our consciousness is a function of our brains. How is that? Where's the it? I don't
The
detect
consciousness is it.
It's it.
It's a wastebasket.
Everything that is true of me is true of my physical body, I would say, except the relationships and the things. But everything that is intrinsically true of me, true of my physical body. So it's not. I'm not proposing Cartesian dualism here, two separate things, but that if you were to describe, as we can describe it now, using biological, physical descriptions, everything about my physical body, we couldn't get out of that description other facts that are true of me.
Most people would look at a Macintosh and say, it's doing this.
What he's saying is that what you say may be true, that, okay, maybe we don't know now because we don't even know all the functions that we need to explain.
Exactly,
Our
I
current
agree.
science is not even wrong.
Exactly.
That's how they would say it.
Exactly. A complete agreement there.
Right,
Yes.
but it's not as if we know that in principle that's not possible.
Exactly. Exactly.
Does it help us at all to think about the problems in building a machine that has consciousness? Just to think about what the issues are there? Does that help us?
That's why I wrote that chapter, because it seemed to me there are a lot of functions you want a mind to have, and when I started cataloging them and trying to get students to program them, I found that there were a whole lot of them, and that the philosophers who talk about it, and like Chalmers and the hard problem of consciousness, they are trying to do the opposite. They're saying, they talk about qualia. What is the quality of seeing red? Instead of seeing this as associations with blood and with, painting and with 100 different things, as though there's a redness. But we know that some women have two reds. There isn't any red. Some people have no red.
And how do we know this about these women? Is it by
Because
the
we do-
description of this
Because
blood?
they have 4 kinds of cones, and when you measure the right thing.
How do we know? But we ask them, when we're asking them, what is the quality of this experience, and how are these reds different? You always have to go to the subject.
They're not
actually.
novelists. You're a novelist, so when you describe quality, it takes a whole book. When a philosopher describes it, they just say, oh, there's a qualium.
Well, if we were to do justice to conscious experience, it would always take at least a novel at every moment.
Sure.
Well, since we've all agreed on consciousness now, what about free will? Anything to say about free will?
So,
No takers, no takers.
Wouldn't it be horrible if there were such a thing?
Well, Einstein would always quote Schopenhauer, right? He said, you can do what you like, but you can't like what you like. So, I like that.
and John Horton Conway just last year proved the theorem where basically he showed that if we have free will, then so do electrons, more or less.
So, I mean, if free will meaning things are not determined, that our actions are not determined, or our states are not determined, that sense of free will. Because philosophers often redefine free will so that it is compatible with determinism. It's known as compatibilism. And that, in fact, it demands determinism. Free will demands determinism. If, in fact, our actions are determined by our own desires, which are themselves determined, but if it's caused by a desire, then it's free. And that's a useful notion of freedom. It also ties in with our notion of responsibility. So if I go in and hold up a bank because somebody has threatened to kill my children if I don't, you could say that my action was not free, or maybe it was free because I wanted my children to live. But in any case, I mean, the action of trying to save my children, this was free, but holding up the bank was not free because it was not my desire to hold up the bank. And so I should not be held morally responsible for it. Basically, we want a notion of freedom that will help us out with the notion of moral responsibility. So if you want to go from one large question to another.
I think we should get the Templeton Foundation to have another festival for this.
Well, anyway,
I'm making my way towards God, but we'll get there in the end. But,
I think the nature of discussion indicates also the magnitude of Gödel's achievement, to return to a theme that Rebecca touched on. Because you see, all these are words. As a mathematician, I can fantasize that someone will prove a theorem that we have free will or that we don't, or that someone will prove a theorem that we have consciousness or we don't. But we're a long way from that. But Gödel proved a theorem with such deep philosophical consequences that 80 years later we're still discussing where does this leave mathematics, where does this leave certainty, where does this leave pure reason. Yeah. So as a pure mathematician, I think that's splendid, and I would like us to do the same with other deep philosophical questions, except I have the clue how.
But does it upset you as a mathematician?
I mean, yes, it does. It upsets me.
That it can't be done.
That's why I'd like to see a theorem proving that Darwinian evolution works or that it doesn't. Because it's so basic, and there ought to be a nice little theorem showing that it works. Otherwise, we're not doing our job.
Mathematicians usually prove theorems that only have to do with mathematics. It's not pure mathematics, a rigorous.
But look at Godel.
Yeah. Godel and Turing are really the only two that did this, that proved mathematical theorems that spill out into philosophy.
Well, let's keep it up. We have their good example. So let's not stop there.
So I'm not sure why Gregory is upset, to be honest, because
I'm not upset.
The fact that because the Gödel's incompleteness theorems showed us limitation of mathematics within mathematics. Gödel's incompleteness theorems did not stop physicists from continuing to apply mathematics to explain the universe. In fact,
But did it make them feel uncomfortable?
No, not at all.
Can I disagree with
So why is
Mario
that?
here?
Why does it not make them feel uncomfortable?
Well, it's because it demonstrated more the shortcomings of formal systems.
Exactly. Not of mathematics.
Not of mathematics as a whole necessarily, of formal systems. Yeah. It's like, you may remember
but that's supposedly what mathematics is, according to the current fashion.
And that's what he showed was wrong.
You remember
but then what is pure mathematics? And nobody knows.
You remember that in
it's
school,
not a formal system,
but it's not a formal system.
In school, Euclid and people and Plato actually were crazy about proving everything with a straight edge and a compass. Anything you couldn't do with a straight edge and a compass was not considered right, and so on. Until, others came and said, wait a second, why do I need these chains on me? I can do things otherwise, and so on. So in the formal system, let me go back to the barber that I mentioned before. So there is this paradox, right, about the barber.
You're not bothered because you're a physicist. We mathematicians, some of us were bothered. And then we solve the problem the way people usually do. If you can't solve a problem, convince yourself that it's not important. Forget about it.
But wait a second. I mean, Gödel solved the problem.
But the problem that Gödel posed is still on the table. What is pure mathematics? Hilbert said pure mathematics is a formal axiomatic system, which I'm going to discover, and that's it. And now we know exactly what it means. Something is true if I can prove it according to these rules. Gödel showed that won't work.
You're right.
So now where does that leave pure mathematics?
I'll tell you.
The answer is nobody knows.
I'll tell you where.
You don't care because you're a physicist.
No. Number one, I'm a theoretical physicist, which means I use mathematics every day. Now, but here, listen. We know that we have a problem with the foundation of quantum mechanics. We have serious problems with the foundation of quantum mechanics. All these things about how does an observer determine the results, and so on. The famous, if a tree falls in the middle of the forest. There is another version of it that I like better, which is, if a man talks in the middle of the forest and there is no woman around, is he still wrong?
Yes.
I knew you would say that. I knew you would say that. No, so we know that there is a problem with the foundation of quantum mechanics. There are actually serious problems with the foundation of mechanics. Has that stopped physics from going on? The answer is no. Have Gödel's theorems stopped mathematics from going on?
Wait a second.
The answer
Physics
is
goes
no.
on as technology, but who cares about technology? The fundamental conceptual issues of the foundations of quantum mechanics are really terrible. And if you're interested in thinking and understanding the world, this is a serious problem. If you're interested only in making transistors and making $1 billion, you don't care. But if you want to understand how the world functions, it's important, that problem. You're too practical.
I don't make transistors.
Gödel was not a practical guy. Gödel was not interested in making money.
I don't have the first notion of how to make a transistor. I try to understand what dark energy is, or if we live in a multiverse. No, so, I mean.
Okay, you're forgiven.
my point is that Gödel's theorems, in spite of the fact that certainly they are of huge import, they have actually not stopped the progress of mathematics either.
And that's an interesting question. How come? That's an interesting question in itself, which I would like to understand better.
Well,
and I don't
Gödel answers,
understand it.
but Gödel himself said, that he was showing the limitations of formal systems to capture everything that we know mathematically, but he wasn't showing the limitations of mathematical knowledge. I mean, he was in his paper, What is Cantor's Continuum Hypothesis, he talks about this, and he says what he's shown is that mathematical intuition can't be eliminated. It can't be eliminated from formal systems. So the question comes back to the mystery of mathematical intuition, which is partly the mystery of the hard problem of consciousness.
Well, yeah, I mean, Gödel himself has some lovely philosophical essays arguing that his theorem does not limit the power of mathematicians to solve any problem. However, if you look at these papers, they are full of words. They look like philosophy papers. And therefore, they're open to discussion endlessly.
Exactly.
The greatness of Gödel's first paper is that it deals with a fundamental philosophical issue, and it settles it via a mathematical proof. Gödel himself was not happy with these essays that he wrote at the end of his life. Some of them he never allowed to be published because he never found any proofs. They were all plausible arguments. They were all words. And so what we need is, in my opinion, is to duplicate. Gödel himself, I think, was trying to find a proof of some of these results. And he never allowed these papers to be published because they were just words. And he was looking for a mathematical proof. So I think that we still need to understand these questions better.
Sure. But when you say that the first paper was so fantastic because he got a philosophical...
You said it. I got it from your book.
Okay.
Your profound insight, I agree with. I got it from your book.
All right. I was going to ask you, but what is that philosophical insight that comes out of the 1931 paper?
Well, mathematics doesn't give absolute certainty because it's not a formal system. That's one way to put it.
I don't think Gödel would agree with that. I think that he would say that mathematics does give absolute certainty, even though it's not a formal system.
Okay, so this is 80 years later, and we're still arguing over what Gödel did or did not do.
Could I ask another question? I think that Michael Atiyah may have said this. I can't remember. If I was a jellyfish at the bottom of the ocean, was that Atiyah?
Yeah, I can repeat that story.
Oh, repeat the story, and then when you've done that, tell me that if you were a jellyfish, instead of being who you are,
I am.
Would you have a different concept of physics, a different concept?
So here is, it's not physics really, it is, the question is, was our mathematics in some sense inevitable? So our mathematics started by the Babylonians and the Greeks and the Egyptians, and it started in particular with two fields, arithmetic and geometry. And in arithmetic, the most basic concept you can think of are natural numbers. 1, 2, 3, 4, 5, 6, right? So you might have thought that there is no way that any kind of civilizations, wherever they are, they would have to come up with the natural numbers. And those are inevitable. So then comes the question, suppose that intelligence resided not in humans, but in some isolated jellyfish living at the bottom of the Pacific Ocean. All that this jellyfish can feel is the temperature of the water, the pressure of the water, the motion of the water. Would these jellyfish have come up with the natural numbers?
And it can't count, there's no fish for it to count.
There is nothing to count. This is why I said isolated. 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 So it's not
too
sure.
many
It's
to
not
count.
sure that it would have come up with that system.
What about pellets of food?
What?
Isn't it eating something?
Yeah. So
Days
So
and
it's
but
nights.
it may be just taking in water and taking whatever goes with it.
Well,
Let's not get lost in the
Einstein has a remark on this that I feel is very deep. Einstein has an essay or two where he says even the positive integers are not a priori. You think they're a necessary tool of thought, but they are actually a free creation of the human mind invented by us to organize our sense perceptions. And this is a quasi-empirical view of mathematics, that we invent mathematics, and that even the most fundamental concepts in pure mathematics are inventions. And this is a view that Gödel discusses, because the two of them talked all the time in those late essays.
Yeah.
But the question,
I call it a quasi-empirical view, following Lakatos of pure mathematics.
So I was trying to go one step further, and you said it wasn't a question of physics, because the reason I was asking the question was because mathematics to us can make so much sense of physics. If I was a jellyfish, would I create a different physics?
Or a different mathematics.
Because I would have a different mathematics.
So the question is, for example, why, you may ask, and that's a deep question, why did the ancient Babylonians start with arithmetic and geometry? And I'll give you why I think. No, that's why they chose a particular number for their base. But the question is why at all to start with arithmetic and geometry? And I'll tell you what I think. This is a personal opinion. I think that this has a lot to do with our perception system. Our perception system, and Gregory just alluded to it, our perception system, we are very, very good at seeing the boundaries of things. I can see that this is the end of Rebecca, and then there is some background, and so on. We're very good at this. This had to do with the fact that we started counting things. We are very, very good at seeing straight lines and curves. We can tell that something is a circle and not an ellipse. Again, because of the way our perception system works. This is, I think, why we started with geometry. Maybe if we saw everything in the infrared, let's say, where all the lines would have been blurred, and so on, maybe we would have come up with a different concept, because we could have started with a different concept.
So this is where absolute truth has gone. It's completely gone nowadays. But Godel believed in absolute truth. And I still think it's a good thing to think about. Even if it's not fashionable, it may come back,
When you mean a good thing to think about, a good thing to take seriously, or just a good thing to ponder upon?
All of the above. I don't quite see the difference,
So Marvin, for example, can tell you that we could have started mathematics with these things which we call cellular automata, which are like little computer programs. You start with a certain small set of rules. You put one white pebble, next to it you put a black pebble, and so on. You can show that you can derive much of our mathematics and physics from such small computer programs.
Well, there is a funny experiment that Danny Bobrow and I did once in the early days of computers. Namely, we wrote a program that listed all possible Turing machines, starting with the very simplest ones. And in the first few thousand of them, most of them did nothing, and some of them did little circles like counting up to 3 and starting over. And a few of them started counting the integers. And in the first I think 50 or 100,000, none of the machines did anything interesting except the ones that counted.
That's interesting. That's interesting.
So in other words,
issue.
arithmetic is among the simplest things
Yeah.
that can happen.
That's a
Yeah,
beautiful
it's lovely.
experiment. You know, this raises an issue, which is the traditional Platonist view is God is a mathematician, the world is built out of pure math. There is a more modern version of this, which Marvin was alluding to indirectly, which is that God is a computer programmer, the world is built out of software.
Yeah.
That's sort of the current reincarnation of that older view.
In some sense, this doesn't seem to me so very interesting. That is that what had to be true of our cognitive faculties in order for us to discover mathematics? Or if our cognitive faculties were different, we could have discovered these structures as well. Or maybe, you know, if our cognitive faculties were so very different, mathematics couldn't be discovered. We would not be able to access it. Doesn't seem to me to address the question of all is, does there exist something independent there to be discovered? Whether we can, you know, it's a lucky fluke that we evolved intelligences that could discover this. I mean, to me, it's amazing that we know anything at all. That we, the products of blind processes of evolution, know anything, can sit up here talking about Gödel's incompleteness theorems or relativity theory or quantum mechanics. It seems to me extraordinary. So the fact that if we had different cognitive abilities, we wouldn't be able to access the few things that we do access doesn't seem to me to get at the heart of the objectivity of what we're discovering.
Probably most planets don't have time because it took about 500 million years. When did life start? Fairly early.
Life started very early.
3.7 billion years ago.
Okay, but planets like this with the sun, we only have 3 more billion years before the sun goes nova.
No, it doesn't go nova, but it becomes a red giant.
Yeah. And so it might be that most planets don't have mathematicians. It's too bad.
So,
Well, there's a pressing question. Let's say we get signals from some other star. So there are these intelligent jellyfish, right, on some other solar system. And obviously we will want to communicate, but we don't have much in common with these intelligent jellyfish. So what can we talk about?
Gödel's theorem.
Maybe Gödel's theorem, maybe the prime number theorem, number theory, maybe logic, maybe philosophy, or maybe nothing, you know. So maybe we have nothing in common. We can just send them cartoons or...
Yeah, I have to just say one thing about
TV programs.
Godel had very little faith in our ability to be able to communicate with one another with words. And that's why he wanted to, although he had these deep philosophical convictions, he never breathed a word of them to these people who were discussing them. He wanted a proof. A proof was and there is this one story I love so much of, he was coming back from a meeting of the Vienna Circle, and he said to another mathematician, Menger, well, I think Menger said to him, tonight we out-Wittgensteined all those Wittgensteinians. We kept completely silent because Wittgenstein ends his Tractatus by saying, you know, about what we can't speak, we must be silent, you know, a lovely tautology. And Godel responded back. He said, the more I think about language, the less I believe that we can talk about anything of interest to one another, that we can understand each other through language at all. I often have that feeling in talking.
But hopefully we haven't shown that to be the case this evening.
There's a whole film, it's called Lost in Translation, which is much
So I want to just come back to you. You asked the question, and Rebecca just touched on it. So are we discovering mathematics or are we inventing them? And I'll give you, this is a personal opinion. And mathematicians discuss this to death. And Gregory will say I'm a physicist, but yes, okay. So
no, Plato says we remember mathematics. Remember Meno?
Yes. So
we don't discover it or invent it.
So here is the thing. When you pose the question like this, was mathematics discovered or invented? I think you have already committed an error. And the error is that when you pose it like this, people immediately assume that the answer has to be that it is discovered or it is invented, and it cannot be something different. Now, the way I think about this is that actually mathematics is an intricate combination of inventions and discoveries. And let me just say very broadly, we invent the concepts and then we discover the relations among the concepts. I'll give you a specific example. There is no square root of -1. There is no number that is the square root of -1, okay? Humans at some point had to invent that concept. They invented the concept. Once they invented the concept, they discovered that there is all kinds of mathematics you can do with that, you know, and so on and this. So you invented the concept, then you discovered lots of things. Prime numbers, which Gregory mentioned.
Wait.
He will disagree in a second.
Can I just give you a perspective from the other side of the wall? You know, there are lots of, we all have to survive in this competitive world, so you have to publish a lot. A lot of the math papers that are published, frankly, look invented, artificial. You know, they are giving answers to questions which really were better left unposed, right?
Yes.
But when you find a piece of mathematics that is really basic, that is really fundamental, you sometimes, maybe it's an illusion, you get the feeling that there was a certain inevitability to it, that you're just discovering something that existed there in the Platonic world of ideas.
That's your feeling.
But most mathematics, I agree,
it's like this. Now,
is not reached this exalted level.
Take even the prime numbers, which is something that is, of course, favorite of everybody's. The Indian mathematicians, Chinese mathematicians, never actually invented the concept of prime numbers. It does not mean they didn't know that prime numbers exist, but as a concept, they did not declare it as such. And when you look at their mathematics, it doesn't appear there because they did not invent the concept. Now, of course, everybody knew that there are prime numbers there. But the fact that Euclid proved that there is an infinite number of them, wrote a mathematical proof, and so on, they became a very, very fundamental part of mathematics. Now, Gregory is going to say, yeah, but we discovered so many things there about them, you know, and so on. They feel like a discovery. Yes, most of them are a discovery, once you decided that the concept is there.
Right, we're nearly at the end. I think I want no more than 1 minute from each of you. No more than 1 minute from each of you on what you think is the major limit of our understanding, starting with Gregory.
The major limit of our understanding? What I do think is that we don't understand Gödel in completeness yet. It's still a challenge to us. The major limit of understanding, complexity perhaps. Some things are too complicated for us. It requires too much information to hold in the human mind. In biology, you start to stretch to reach those limits, and so I think complexity is a very important limit.
Rebecca.
Oh, where does one begin? There are just any philosophical problem measures the limits of our understanding. I think my field, philosophy, is what it is all of the problems that we are smart enough to ask, some of us, and I mean it's really the hard thing is to even understand what the problems are, just smart enough to ask and not smart enough to answer. So just go to philosophy and you will find all of the limits of our understanding.
Mario.
I think that right now what I see as the most major limit to our understanding is the fact that we cannot quite know what is truly fundamental and what may be just accidental. Kepler thought that the number of planets in the solar system was a fundamental thing which he needed to explain from first principles. Today we know that's not the case. It may be that some of the things that we now perceive as fundamental are not really such, and they are accidental, perhaps in a multiverse, that we happen to live in a universe that has such things and so on. I think that the fact that we don't know this distinction is a major limit to our understanding.
Marvin.
Well, I have slightly different answer, which I would hope that Chaitin and Rebecca would agree with. Well, Chaitin will. It seems to me that the most important discovery since Gödel was the discovery by Chaitin, Solomonoff, and Kolmogorov of a concept called algorithmic probability, which is a fundamental new theory of how to make predictions given a collection of experiences. And this is a beautiful theory. Everybody should learn it. But it's got one problem, which is that you can't actually calculate what this theory predicts because it's too hard and requires an infinite amount of work. However, it should be possible to make practical approximations to the Chaitin, Kolmogorov, Solomonoff theory that will make better predictions than anything we have today. And everybody should learn all about that and spend the rest of their lives working on it.
I think this evening we've learnt one thing at least, that there's very little limit to the understanding of our panelists. Thank you very much. I think we go, ladies and gentlemen. I think we